Okay, good afternoon, everyone. So I will talk about event filter tracking for the phase 2 upgrade of the Atlas trigger at high luminosity LHC. And to give you an outline of the talk, first I will start with a bit general discussion on what has changed in the design of the tracking reconstruction in the trigger since the TDAC TDR in 2017. I will talk about a bit more details of the tracker reconstruction, fast tracker reconstruction on CPUs. Then say a bit on possible use of accelerators, and I will conclude with next steps what we are working on. Most of the material I will present comes from the amendment of the TDAC TDR with respect to the event filter tracking, and it's linked from this page. So let me start with the timeline of the LHC. So basically, we are starting these days run 3. The run 3 will last until the end of 2025. And from there on, there will be long shutdown 3, which will upgrade the LHC accelerator and also will upgrade the detector systems to be able to cope with new conditions. The peak luminosity after the upgrade in the run 4 will double originally, but it will go up to almost factor of 4 at the end of run 5, and this will bring in pile up conditions of 140 in the beginning up to 200 towards the end. So we need to do upgrades of the detector and of the data acquisition system to be able to collect data in these conditions efficiently. One very important upgrade from the Atlas side is that we will upgrade the current inner detector, which combines pixel strip and transition radiation tracker technologies with a new detector, IDK, which is solely silicon-based and provides multiple measurements of tracks in silicon. So what is the Atlas event filter? So you can see a diagram of the TDAC, of the upgraded TDAC on the left hand side, and the event filter is the box at the bottom. It's a processor farm which is responsible for forming the trigger decision after the event has been accepted by level 0 accept. So we will process about 1 megahertz of level 0 output, and out of the 1 megahertz we can select about 10 kilohertz of events for storage. And the major part of the processing which will happen on the event filter farm will be spent on tracker reconstruction. There will be several hundreds of kilohertz on the regional tracking for lepton triggers, about 150 kilohertz dedicated to full scan, the reconstruction in the entire region of the IDK, and this will be used for jet reconstruction, ET-maze, P-flow. And last but not least, we will also look for more exotic signatures with the large radius tracking. So what is the evolution of the tracking solution for the event filter? So in the technical design report in 2017, it was assumed that this will be provided by a custom hardware-based system combining memory i6 and FPGAs, and this system will be capable of reconstructing tracks in the conditions of very high pileup. And several parameters of the TDAC system were driven by the plan that the system will actually evolve into level 0, level 1 system capable of processing a higher input rate, 4 megahertz with respect to 1 megahertz, and that it will deploy track information in the level 1 decision to reduce the rate. So these requirements made the system more complex, and it was recently decided that we will actually not pursue the evolution scenario. And in the light of removing these low latency requirements, we could also revisit what the solution for the tracking in the event filter will look like. And what was taken also into account is that there were advances in the speed of the track reconstruction in ITK. There are trends in the industry for heterogeneous computing systems that the programming of these systems gets simpler, and also the projections of the commodity CPUs and commodity accelerators, the cost of the commodity CPUs and accelerators. So how does the new EF tracking system look like? So we will use commercial systems with CPUs and possibly accelerators, not only providing the complete solution by one of these technologies, but possibly also having a heterogeneous solution for the tracking. So what this means in terms of development, we need to optimize the basic blocks of the tracking reconstruction, the data preparation, seeding, and pattern recognition, track extensions, fitting, and ambiguity resolution in the implementations for a CPU or accelerators. And in the next years, we will develop 2 generations of demonstrators for all of these technologies, CPU, GPU, FPGA, and the decision of the technology will be done in the 2025, so that we know the system designed before the start of a long shutdown state. And the decision will be based on fact that whether the system can fulfill the requirements on the tracking performance in terms of efficiency, resolutions, and fake rates, that it can process the events we want to process from the physics menu point of view, that it fits into the constraints on the power consumption, and also the cost of the system. So let me say a bit more on the IDK detector. So the detector has been optimized since the TDEC TDR, and now it has a simpler layout with ring design and inclined better sections, and it's optimized to provide the trajectory measurements at the suitable points in space. So this allows to reduce the consumption of CPU in the reconstruction. And what is also important that the detector has a minimum 5 layers of pixels. If you look at the figure on the left, so you can see that this is very important for a redundancy in seeding and efficiency in the seeding. On the right hand side, you can see what we expect as a number of silicon hits on track, again as a function of eta in the detector. So this is typically almost 15 and higher in the end caps. So the design of the and optimization of the IDK is very fundamental for faster track reconstruction. So what are the key ideas for the fast tracking prototype for the CPUs? So as mentioned in the previous slide, it's the pixel only seeding. The redundancy of the detector allows us to do this. Then we omit the stage of the tracking, the ambiguity solver, which deals with scoring of the tracks and trying to disentangle where hits belong if they are shared. So this functionality can be moved to the track finding and also compensated by tighter track selection. We have faster Kalman filter for parameter estimation. The calibration precision is the same, but it has an approximation in the material model. And the table summarizes the cuts between the fast track reconstruction and the default reconstruction. So you can see that it has tighter requirements on the number of hits, requirements limiting the number of share hits, and increasing the PT threshold in the central region, and also limiting the Z range from where we consider tracks. So these are the main changes. If we compare, or as a side note on how this compares to the run 2 and run 3 reconstruction, so we actually have a good experience with running without the ambiguity solver. The run 2 system worked in 2 stages. In the fast tracking stage, which did not include the ambiguity solver, and the tracks were only defined by so-called precision tracking using the ambiguity solver. So we already did the decision on the tracks without ambiguity solver in a run 2. The pixel-only seeding, it's a bit more delicate in the current detector because the redundancy is not that good and the detector is aging. But if we can tolerate smaller inefficiency, we can also use pixel-only seeding. And you will hear more details in the talk of Jonathan Long on the run 2, run 3 tracking, and examples actually how the limiting of, for example, the Z range increases the speed, how limiting the seeding options also increases the speed. So from the ideas to the performance. So the performance, we see that it is stable as a function of the pileup. There are no big differences between the performance on a pileup 140 and pileup 200. We can see on the left plot that the turn-on is slightly slower in PT due to a higher PT threshold in the fast track reconstruction. And we can also see lower efficiency at higher eta as a consequence of the material approximations, but you can see that the difference in efficiency is maximum is about 2%, not more. As we omit the ambiguity solver, you can ask whether it does not have a negative impact on the number of fake tracks. So this we can see from the plot on the right, where we see number of reconstructed tracks in eta, and compare the number of tracks for the default reconstruction and fast reconstruction. And it's very similar. It's very similar amount of tracks. So the fake rate is also similar. And in terms of the track quality, you can see the composition of hits on tracks for a pixel detector on the left and the strip detector on the right. And again, the number of hits we see on tracks is compatible between the fast and default track reconstruction. I'm sorry. I managed to jump to the end of the talk. So the last on the performance are the resolution. So you can see the resolution of D0 resolution for a 2 GeV muon and 100 GeV muon on the right. And again, there are similar comments to what I made before. The precision gets worse in the forward region due to approximation in the material, and there is also the resolution is also worse for the higher PT tracks. I did not discuss the reconstruction for electrons. For electrons, the plan is to use the Bremer-Were reconstruction. But to use it in the regional tracking to control, not to use it on all tracks, but only on tracks where we expect electron candidates. So this was a reconstruction in terms of performance. In terms of CPU, you can see the results in the table. Basically, pileup 140 and 200, you can see that the improvement is about a factor of 4 in both cases. The biggest contributions come from the omitting of the ubiquitous solver and the improvements in the track finding coming from also from the seeding, reduced seeding. But you can see that there is also non-negligible contribution from the other terms. And if we compare the reconstruction time with a default reconstruction and an earlier design of the layout of the detector, we can see actually a factor of 8 at pileup to 200, which is very, very impressive improvement. What I did not discuss so far is the large radius tracking. This is second pass after the fast tracking reconstruction. This is implemented as a second pass after fast tracking reconstruction, and it's using seeding from the strip detector, and then goes on with the standard tracking reconstruction, but with adjusted cuts to serve the purpose. So you can see that. There is a higher PT cut, and also the limits on the D0 are different to the standard reconstruction. And you can see the efficiency comparison of the efficiency between the default and fast tracking reconstruction in blue, and how basically the fast tracking reconstruction goes down as a function of production radius, but it's compensated by the increase of the fast reconstruction with the large radius tracking. The cost of the large radius tracking, if we compare again on TT bar events with the pileup 140 and 200, it's not negligible. We had something like 30 for pileup 200 for the fast tracking, so it's about 1/3. But the plan is to run it in a regional way, and also not on all events, so we would control the input rate to this reconstruction. So let me move to the accelerator demonstrators as a part of the preparation of the TDR amendment. It was also studied the feasibility of using accelerators, FPGAs, and GPUs, and there was a demonstrator of the FPGAs using a half transform for pattern recognition. So exploring the fact that the tracks map on lines in the 1/PT and phi plane. So you can see an example how it looks like for a single and muon and muons with pileup on the right. So this was one demonstrator. Second demonstrator was all GPU, where parts of the reconstruction were running on GPU, data preparation and seeding. If we see what the performance of the FPGA of transform demonstrator was, you can see that it was very good for muons in all. This is the top row with in different regions of eta. There was a degradation of performance for pion in the forward region, but this is something to be optimized further, and also improved implementation. So these were technologies, but how we will put this all together into an implementation of the EF tracking in Atlas. So we are planning to use ACTS project. It's a open source project to develop a general track reconstruction software, which is not limited to a single experiment. The implementation is modern and also portable with respect to accelerators. So there are many contributions related to ACTS at this conference, so you can see lots of is happening on this front. And Atlas plans to migrate the tracking reconstruction, both ITK and muon reconstruction, to ACTS. And on the EF tracking side, we also want to use ACTS framework and use both CPU or accelerator implementations from there. Just to know that if we go for a heterogeneous variant, we have to have a suitable model for the data, where the transfers of data between technologies do not slow down do not reduce the throughput of the implementation. And this is something which is being worked on right now. So this brings me to the summary and outlook. So we are working on the redesign of the EF tracking for a phase 2 upgrade of the detector. We are planning to use commodity systems, so this is a difference with the original plan. And during the course of the preparation of the TDR amendment, CPUs, all three systems, CPUs, GPUs, or FPGAs, were identified as a viable solution to the problem. With the fast tracking, which was most advanced at the time, we demonstrated that this is a possible solution and fulfilling the requirements, and there was a speed up of 8 demonstrated in this prototype, and there were initial demonstrators also for accelerators. So there is ongoing work, and there will be more work on demonstrators, on 2 generations of the demonstrators before 2025, when the choice of the technology will be made, and we need to demonstrate that these prototypes can deliver performance as required by the TDR. And that they can fit in a cost budget and in a power consumption budget. And we plan to contribute and also benefit from other developments which happen in the ICTS project, and use it both on software or accelerated solutions. That's it from my side. It looks like I made it faster than.
Keep clapping, because I just unmuted now, so you can hear it. Are there any questions in the audience? So I already have a question. So you were mentioning well, obviously you're mentioning CPUs, GPUs, FPGAs for the viable solutions. What sort of technologies are you using to code this? So the FPGAs obviously are going to need some sort of OpenCL or some sort of language to be able to basically program the boards, and then same with the GPUs. How much overlap do the algorithms have, and what technologies are you using, etc.?
So we would use some sort of solution like SQL, but we will certainly build on what is available and what will become available in the ACTS, in the implementations of TrackCC, in Ditray, and so on and so on. So we plan to not develop from scratch, but rather try to reuse what will be available in ICTS.
Okay. So trying to pick things that will be also compatible with ACTS. Okay. Any other questions, or any questions in the room? Okay. If not, thank you again, Yuri, for this very nice summary.